This is a practice exam for Exam 3 in Astronomy 305. Here's some example questions, and notice that you'll need your textbook for the exam, so make sure that you bring it to the test. And also, I would recommend getting some yellow post-it notes and posting them on the appropriate pages so you can more easily find these equations during the exam. This is on page 66, section 32, talking about the angles between celestial objects. Looking at this first one is the angle between Betelgeuse and Rigel, and just make sure that you convert that over to decimal hours first, and then multiply it by 15 degrees per decimal per hour of right ascension, and then you'll record the answer right here in decimal degrees using that format right there. This one's a little easier because you're converting degrees, arc minutes, and arc seconds over to decimal degrees here. Doing that also for Rigel, for right ascension and declination. So alpha is right ascension, delta is declination. If you have all four of those in degrees, then this equation right here will work. It will allow you to find the angular distance between one celestial object and the other in degrees. So make sure your calculator is in degree mode. When you calculate that, make sure you use the format like this for all five of those answers. Looks like it's 6 digits past the decimal. And also make sure that you have units for every answer on this practice exam, or the exam itself. If you look at number 2, it's talking about the rise azimuth of a star, the angular around the horizon from north measured toward the east. That's A sub r for the rise azimuth. And we're looking at two different latitudes on the Earth. In particular, we're looking at this equation here, and it talks about nu in the narrative on this page. I don't have the page number captured in this image, so make sure you look through your homework or the book itself, find these equations, and mark it with a post-it note before the exam. You'll notice in this section right above this equation that nu is the angular displacement of a celestial object caused by atmospheric refraction. And on the homework and also on this practice exam, we are assuming that that nu is going to be 0. We'll say that it's negligible when we're just trying to find the approximate rise azimuth of the sun on the day of the summer solstice. So in that case, you're going to use a declination of 23.5 degrees for this one right here and that one right there. The difference is sunrise and sunset. There's a rise azimuth, and there's the set azimuth here. This is the latitude, and you can see that the latitude is in the equation as V right there. For the winter solstice, the declination is negative 23.5 degrees. And then for the autumnal and vernal equinoxes, the declination of the sun is 0 degrees. Plugging all of that in, you should be able to get some answers here. You might get some unexpected answers here for 75 degrees. I want you to try to think about that, visualize it. Maybe have a sketch that will help you understand it. I think you're going to find the case where if you're so far north, either the sun doesn't rise or the sun doesn't set. So look for those cases and try to determine which one it is. Is it a case where the sun never rises or the sun never sets for the solstices and equinoxes? Moving on to question number 3, it talks about atmospheric atmospheric extinction, where we're talking about the dimming of light by an atmosphere. And the dimming of light by the atmosphere has its least effect when you're looking at an object at the zenith. That's the location. So where in the sky it is the effect the least? Directly overhead. And the explanation for that is because the light path of a star is least if you're looking at it directly overhead. Otherwise, the light path has to go through more atmosphere, and therefore the direct beam, more of the direct beam is scattered out, and the star appears dimmer. The equation for finding the change in magnitude of a star due to the atmospheric refraction looks like this, and you can see that Z is the zenith angle, the angle from the zenith over to where the star is. And the connection between the zenith angle and our familiar A altitude is Z is equal to 90 degrees minus A. That's the connection between all of those. So looking at the case, if you're outside of the atmosphere, you would have no dimming at all for this 3.861 magnitude star as seen from International Space Station, in this case, of Beta Victoris. But then, if you let that starlight go down onto the ground and you look at the object directly overhead, it'll drop by about 0.2 magnitudes, but it's not looking for the case where it's 90 degrees. It's looking for um, altitudes A of 15, 30, 70, and 80. So you'll first have to use these A's right here to find the Z. The Z goes right there, and that tells you the change in magnitudes, the adjustments that you make to the 3.861. If that didn't make sense, kind of maybe play the video again and kind of go through this and carefully read it to determine what these four values are. Moving on to question number 5. Now you're looking at the case of atmospheric refraction. In this case right here, we have a star. It is fairly close to the horizon at 10 degrees, which means we don't use this approximate formula, but instead this more precise formula. And you'll have to plug in the altitude of the star in degrees in this right here. So we're not going to assume that those A's are 0. As it says up here, the altitude of the star is 10 degrees, the azimuth is 265 degrees. So if the true altitude without atmospheric refraction is 10 degrees, then what will happen is the star will appear slightly higher by an amount r for the apparent altitude. And then just like we did for the previous problem, the zenith angle is 90 degrees minus the altitude. So notice the true zenith and the true altitude are connected. In the same way, the apparent true zenith angle is 90 degrees minus the apparent altitude. The thing about these last two questions about azimuth is they're going to be unaffected. Atmospheric refraction only causes stars to appear slightly higher in the sky. There's no left or right adjustment because caused by atmospheric refraction. Therefore, the answer to these last two are simply 265, simply because atmospheric refraction shifts up and down, but not left and right. Going on to question number 6, just make sure you go over to the course home page, review some of the Java simulations that we did for binary stars. I got some extra ones down here that you can take a look at. This one has an animation where you can adjust eccentricity, star masses, making the second star heavier. You can speed up the animation, play around with it a bit, increase the radius, and notice the effect on the light curve as we start to change the size of the stars. Also, you can change the surface temperature, and that changes the depth of the eclipse in each of these cases. Even increase or decrease the separation distance between the stars. So just make sure that you read these questions carefully and put in the parameters carefully when you run the simulation during the exam. And make sure that for spectral types you answer in these blanks here, O, B, A, F, G, K, or M. So you want to have single letters in those two blanks for the two types of stars that led to that shape of a light curve. And when the sizes of stars are quoted here, make sure that you put a number there. Include units like solar radii, because that's relative to the size of the sun. So a 15 solar radii star means that it's 15 times the radius of our sun. Looking down on this one right here, you're adjusting the inclination, so make sure you put an answer here in degrees. For what range of inclinations, you want to have a beginning and end value for that blank. When you look at this simulation right here and you change the spectral types to B and F, what you might find in the simulation that we ran over here, this one right here in particular, you're going to find that if you run that simulation, it's impossible to have those two spectral types along with a separation of 5 solar radii, simply because these two stars would be overlapping. So the simulation would be incorrect. I'll let you run that simulation so you can see that it's kind of an impossible situation. If you assume that these two stars are spherical, they're just not going to be enough space in between the two stars to generate a light curve that is realistic. When you're starting to look at the things that you can list, which you can learn from a light curve, you can see that what they are is listed up here above. You can learn things like orbital inclination, the surface temperatures of stars, their spectral types, their relative sizes, and the ratio of the masses between the two stars. Those are just a few things that you can learn by studying the light curve of eclipsing binary stars. And question number 10, if you look in the section on page 123, you'll see this table, and it has information for Mars, its orbital elements, which includes E, the eccentricity. On the next page, 124, you'll see that you can find the distance equation. This will tell us how far from the Sun any planet is based on its orbital parameters. Lowercase a is the semi-major axis, which can be found here. The value here for the Earth is about 1 astronomical unit, or 93 million miles. In the case of Mars, it's 1.53 AUs. That would go right there. If you were calculating the distance from the Sun to Mars in astronomical units. E is the eccentricity. You can see that it's a little bit eccentric with a 0.0933 eccentricity that goes here. Nu is the angle around from the closest point of approach in its orbit, around its orbit. So nu right here, this Greek letter nu, goes from 0 to 360 degrees. That means that you'll get a maximum and minimum distance from the Sun, a close approach and a distance approach. And that's called the perihelion and aphelion. And recall that those correspond to nu being 0 or 180 degrees. So again, perihelion, aphelion, nu is 0 and 180 degrees. All right, so that will allow you to calculate those distances. In reality, what you would do is on a particular day is calculate what the nu is, plug it in, and then you would find out for that moment in time what the distance from Mars would be from the Sun. On the last few pages here, there's a question 11 that says, what does CCD stand for? It's a charge-coupled device that basically is used in imaging. It is a chip, and here's what the chip looks like up close. In this case, I have a square one, and there's tiny little photosites right here, maybe thousands of those this way and thousands of them this way, making a large array. Each photosite is light sensitive. When a photon hits it, an electron is freed up. And it's those electrons that are brought off to the side using registers to kind of read them off and then generate an image that's of the light that's being incident upon that chip. So it's a major piece of technology used in digital imaging. If you purchase, say, 4 megapixel camera, it means it has a chip that has 4 million pixels. So the mega means million, and the 4 here, 4 million pixels. And the only way that that could happen, really, if this is square, is if you say take the square root of 4 million, and you'll find out that there's 2,000 pixels this way and 2,000 pixels that way, giving you 4 million photosites from which you're capturing an image of an object. And you might even look at the number of megapixels in your phone or digital camera to see just how many millions of photosites these cameras have. As we saw during Night Lab, the dark frame image is obtained by taking a picture with the shutter closed. The exposure time should be the same length as the exposure of the celestial object. For example, we took a 30-second exposure of the Orion Nebula and a 30-second dark. We also did the same thing for minor planets as well. In question 14, it says, what is the purpose of taking that? And as we've learned through analyzing stock images during our lab preps, we learned that dark frame subtraction is a way of minimizing images, minimizing image noise. And what you do is, again, take a long exposure that matches the light exposure, and it takes advantage of the fact that the image that you see here is the same for each shot that you take. There's the same kind of noise, even these streaks that you see here, and the pixel-to-pixel differences in sensitivity. This takes into account dead pixels, which are pixels that are not as sensitive as their adjacent pixels, and also hot pixels, which are more sensitive. So it takes advantage of those, and you subtract off the noise from the raw image to obtain a better photograph. In the same kind of way, a light frame image is a way of making the image more about what's in the sky rather than what's inside the camera or what's inside the telescope. A flat field image is obtained by taking a short exposure, maybe 1/10 of a second, of a uniformly illuminated white screen. And what we did was we positioned that at the end of the telescope, took a 1/10 of a second exposure, And we saw that the shadows of the dust on the lens of the camera itself, the CCD camera mounted on the telescope, had little dust grains on it, and it caused these donut shadows on there. We also see that there's some brightening in the middle and dark toward the outside edge. That's because of the structure of the telescope being round, but the CCD camera being rectangular in shape. You'll even see these streaks right here showing the differences in sensitivity of the pixels as you go from one pixel to the next. So if you do a dark subtraction, that removes some of the noise, and you do a flat field correction, and that is used to improve the quality of the digital image. The goal is to remove artifacts from two-dimensional images that are caused by variations in pixel-to-pixel sensitivity of the detector, and we're talking about distortions in the optical path. That's the dust grains that we're talking about here, and the so-called vignetting, which is the darkening of the outside edge and the lighter part in the middle here. It's a standard calibration procedure in everything from pocket digital cameras to giant telescopes. All right, I hope this was helpful. Feel free to send me an email if I can help with anything further.